Hello and welcome back for lesson 2.7. Today we are going to learn two measures of the spread of the data. So the first one we're going to look at is the range, and you've probably been exposed to this before in another class, but the range is the measure of distance between the largest and smallest data values, and we're going to calculate that as the maximum minus the minimum. We are also going to look at something called the standard deviation. It is the number on average that measures how far data values are from the mean. So let's look at two sets of data so that we can see the importance of the standard deviation and the range and measures of spread. So we're going to look at an algebra exam, so how students performed on an algebra exam versus how another set of students performed on a stats exam. So let's go to our Desmos link. And in our Desmos link, we're also going to see, we're going to use this dot plot. So we can see on the dot plot that our students here on the algebra exam, and then here's our students on the statistics exam. But let's go ahead and find their mean and the range in Desmos of each of these sets of students here. So in Desmos, I have the exam data for the algebra exam here on the left and the stats exam in the Y. And I'm doing a box plot of both. And you can see here that the spread is much different between the two. So the algebra students have a minimum of 60 and a max of 100, and actually so does the stats students. They both have a min of 100 and a max of 100 and a min of 60. So their range is 100 minus 60 equals 40. So they have the same range. And let's go ahead and find the mean of both. So the mean of x1 and the mean of x2. I'm sorry, y1. There we go. Oh, they both have the same mean as well. Okay, so let's make sure we write that on our paper here. So it looks like they have the same range. So it appears they have the same spread and the same center, the same mean. If you take a visual look at the data, it does not look like that. From the data, it looks like the algebra is much more centered around the mean. So if we were to plot the mean would be somewhere around here. And it looks like the statistics students are really not centered around the mean. So for the algebra students, I would say the mean is probably a good measure of center. There is a student that scored high and a student that scored low. But in the algebra set, it looks like they're much more spread out. So let's look here. This should be B and C. It says that the means of two data sets are the same. Does that mean the data sets are similar? We could say not necessarily. Because these have the same mean, but they're definitely not similar to each other. If the ranges of two data sets are the same, does that mean that the data sets are similar? And I would say not necessarily on that as well. So let's just go ahead and calculate for the statistics students, because it seemed like their deviation was deviation or what they're spread out is much more. So we're actually going to calculate what's called the deviation about the mean. That's the difference between each observation and the mean. So we're taking the X observation and subtracting the mean. So X minus the sample mean. The sample mean was 74. So for example, the first one is 60 minus 74 is a negative 14. And then we're going to have 100 minus 74, 61 minus 74. So this would be 26. This is going to be a negative 13. Is a negative 9. 85 minus 74 is 11. 16. Okay, if we were to add these deviations, let's just see, let's say if we added these deviations, what would they add up to be? Let's go ahead to Desmos and do that. So let's just add plus 26 minus 15. Oh, if we add them, they add to 0. Does that really mean that our deviations are 0? Because if we average them, then the average would be 0. That's what this says. But that's definitely not what we can see from the picture, because the deviations visually, you can see them from the mean. Here's a deviation. Here is a deviation. Here is a deviation to this point. Here's a deviation to this point. Here's the deviation to this point and to the min. So we can visually see that there's deviations. Well, maybe it's because all of the negative deviations outweighed the positive deviations. So what could we do to get rid of any negative deviations? We could square them. Squaring all negatives and positives will result in a positive value. So we could take this x minus the x bar. We could take that and square each of these deviations. So we're going to square each of them and then add them together. That's 196. That's 676. That's 169. That's 256. So if we were to square these deviations, which we did, and add them together, then we could average them. That's what we're doing in here. So we want to find the average deviation because that would tell us about how far. So if we do that, what we're doing here is when we find this average of the square, we're actually finding the variance. It's the average of these squared data. So if we were to go into Desmos and put in these individual deviations, and here we're just going to take x2 and square it. Okay, and square it. And then I'm going to average those. So I'm going to take the mean of x2 squared. Oh, I got to square it inside here. Okay. So the average is 175.6. That is going to be our variance because they're still squared values. So the 175.6 is not going to look like anything like our actual deviations, but it is squared. Then we could take the square root of that, right? Because that undoes the squaring. So let's do that. Let's go down here and choose the square root button of 175.6. And then we get back to something that looks much more like a deviation, 13.25. Well, I can tell you, my friends, that we are not going to do any of this by hand for the semester. We're going to use a function here in Desmos called standard STDEV is going to be for the sample. So we would take x2, and then we're going to do STDEVP of x2 for the population. And so that's why the population came out to be 13.25. So I'm just going to make a note in here for you all that this is the sample standard deviation. And the sample standard deviation is taking into account that we are approximating because we don't have is different than the population because we have a sample. Okay, and then the population is down here. So the population, the sample standard deviation is going to be divided by n minus 1, and that's why it's a little bit different. So had I divided by n minus 1 here, when we did the mean, we would have gotten this 13.96, a little bit bigger number. So we will never calculate this by hand, but we will use Desmos to do that for us. So let's go back to our paper momentarily so we can see. I'd like to show you the symbols that we're going to use for the variance and standard deviation here. So just one moment here. Back to our notes. So back to our notes here. So for the variance, we are going to use sigma. This is called sigma, this little symbol here. It's sigma squared is the population variance, because remember, everything is squared. The population symbols are always Greek letters. The sample symbols are always just a letter in the alphabet, so we're just using an S. And then the standard deviation is the square root of the variance. So to go from the standard deviation to go from the population or the variance to the standard deviation, we're going to take the square root of the variance. Okay. And to go from the standard deviation to the variance, we're going to square the standard deviation. And that's what that will look like. Okay, so let's look at our first example here. So let's go back to our statistics data once again, and we're going to look at the population. Let's start with the standard deviation because that's what comes out of the Desmos anyway. So let's go back to our Desmos here. So the population standard deviation is the STDEVP, and that is 13.25. So let's write that on your paper. 13.25, and that has a symbol equal to sigma. And then the population variance, we're going to calculate just by taking that 13.25 and squaring it. And so we get 175. So the population variance is sigma squared, and that's 175.56. And then our sample standard deviation is just the STDEVP right here, 13.968. So let's make that 13.97 is a sample standard deviation. So that's just S 13.97. And then the sample variance can be calculated as 13.968. I'm gonna use the decimals there just to calculate the square, so it's more accurate. And so that is S squared, and that's 195.1. Now, our variance will not have any units, but our standard deviation does have units. And so if we go back to our notes here, go back to our notes, it says which variance and standard deviation, population or sample are more appropriate in this situation. And that would be sample, because we only have a portion of the student data. And then it says, is the answer for C a parameter or statistic? And that's the sample standard deviation. And that's a statistic because it's coming from the sample. Interpret the mean and standard deviation for the statistics data in the context of the situation. So notice down here, I've got kind of a formal way of writing that. And I would like to make sure that you're using this formal way. And so we're going to write that out. So we're going to say on average, the statistics students scored 74, give or take, and we're going to use the standard deviation in units. And so the sample standard deviation we said was 13.97. We're going to write give or take 13.97. And that was probably a percentage is what they use for units on that exam. So make sure you're giving the value and the units. And so on average is what you're going to use. Then you're going to talk about the context. You're going to give the mean and the units. And then you're going to write give or take. Give or take is what is describing the word standard deviation. You won't actually say standard deviation. And then you're going to give the value of the standard deviation along with units. Okay, let's look at our next piece of data. It says on a baseball team, the ages of the players are as follows. Use your calculator or computer to find the Desmos, the mean and standard deviation. We're going to use Desmos. Then find the value that is 2 standard deviations above the mean. Okay, let's go to Desmos. So we're going back to Desmos and we're going to click on the baseball player ages. And I've typed in the ages for you. Make sure that you're practicing this. We asked for the mean and standard deviation. So the mean of X3, that's where our data is their average age. The mean is 30.68. And this is every age of every player on the baseball team. So this is going to be the mu, the mean that is the mu, the population mean. And so that means our standard deviation needs to be STDEVP for the population standard deviation. And that's 5.97. And that's a sigma. Okay. Then going back to our paper here, we are writing our up here. It's asking us for the mean is 30.68 and the standard deviation is 5.97. And they asked us to find two standard deviations above the mean. So above the mean means I'm going to take the mean plus 2 times that standard deviation. So 30.68 plus 2 times 5.97. So I'm going to do 5.97 times 2. So this is going to be 30.68 plus 11.94. $42.62. Okay. The next data set that we're going to look at is we did a sample of different types of food at pet stores in the area. And we want to know how many different types of pet food does each store carry. So there are 1, 2, 3, 4 stores that carried 6 different pet foods. And there were 1, 2, 3, 4, 5, 6 stores in the area that carried 12 different types of pet foods. That's a lot. Calculate the sample mean and the sample standard deviation to 1 decimal place. So we're just getting practice with this in Desmos. And in Desmos, you can see that I have already put in the data for the number of pet foods at a store. And here they are. And the mean is 9.28. 1 decimal place would be 9.3. So the mean is X bar because this is a sample. So 9.3. And then the standard deviation is S because it's a sample, 2.2. So let's just make sure that you're using these correct symbols, X bar and S. Okay, so now we're going to put our mean and our standard deviation kind of all together here. So if our data, we're going to call it bell-shaped, if it's symmetric, meaning, right, the mean is approximately equal to the median here, right, then we can make some statements about our histogram that we're going to draw. So we can say if we were to do the mean of the data, mu or X bar, whichever you have sample or population mean, about 68% of your data points will lie within 1 standard deviation of the mean. So that means if we took our mean and subtracted 1 standard deviation and added 1 standard deviation, 68% should fall within here. And if we want another standard deviation below and above, we should have a total of 95% of our data. And if we were to go out 3 standard deviations, we are at approximately 99% of our data. This is known as the empirical rule. Okay. The empirical rule is right here. So we're just drawing it with the 68%, the 95, and the 99.7. Some books will say 99%, some will say 99.7%. Okay, and because it's symmetric, then we can say that about half of our data, 50%, will fall to the left of our mean, and half of our data will fall to the right of our mean. So let's look at an example of how this might look. It says, in a survey conducted by the National Center for Health Statistics, the sample mean height of women in the US ages 20 to 29 was 64 inches with a sample standard deviation of 2.75. Assume that the heights of women are normally distributed. Because we're assuming they're normally distributed, we're assuming that we can draw this curve. Construct an accurate normal distribution with the parameters and percentages labels. Parameters meaning the mean, so either the mu or the x bar, and then the standard deviations in the percentages. So I want to show you the percentages are always going to be the same. It's the values of your variable, the variable parameters that are going to change down here. Okay, the percentages will all stay the same if our data is symmetric. So let's draw our first one here. Okay, so the first thing I'm going to draw is my center, and that's going to be a sample mean because they had sample data. So the sample mean was 64 inches and the sample standard deviation was 2.75. So that sample mean is going to go down here at the center. And then we're going to have approximate bars here for our percentages. And so for us, the heights are going to go along here. And we are going to go from smallest to largest because it's going to be treated like a number line. Okay. So our percentages, like I said, are going to stay the same. So let's just fill in our percentages based on what we learned from the prior page. So 34% and 34% are going to fall within one standard deviation. So if we take 64 and subtract 2.75, we will get 61.25. And if we add 64 plus 2.75, we will get 66.75. So 68% of our data should have women. If we look at those women that were actually in the sample, 68% of them had heights between 61.25% and 66.75%. 61.25 inches, sorry, and 66.75 inches. Okay, so let's go out another standard deviation. So we're going to add 13.5% here, and we're going to add 13.5% here. And we're going to subtract another standard deviation. So let's just go to Desmos for a moment and look at this. So we are going to take 64 and minus 2.75. That's one standard deviation. And then 64 minus 2 times 2.75 is the second standard. Oops. 64 is two standard deviations. So that should be 58.5. And then if we we go 3 standard deviations, it will be 55.75. And that is the same as going 64 minus 2.75 minus 2.75 minus 2.75. Okay, I just did it 3 times. And then likewise, we're going to add those. So I'm going to do the same thing down here, but by adding. And we're just going to copy that and add. So 2 standard deviations above is going to be at 69.5. And I will show you what it looks like on our graph here in just a minute. So let's just do the calculations together. And the last one, 3 standard deviations, is at 72.25. I'm going to show you these on my graph right now. And then there's 2.35% here. And then the last little percentage is the smallest, it's 0.15%. And it's hard to write because there's not a lot of space. And one piece that's very important is to acknowledge where would those outliers be, because we talked a little bit about outliers in our box plots in earlier lessons, and it's like, where would those be? And so anything that is outside of 2 standard deviations, this is 2 standard deviations, and this over here is 2 standard deviations. So anything outside here would be unusual. And anything outside here is unusual. Okay, so there, it's important to be able to acknowledge that. Where is something unusual? Okay. So let's use this graph that we just made, this normal graph, this using the empirical rule, this bell-shaped graph, to answer some questions. So the first question says, estimate the percentage of women that are between 64 and 69.5. So 64 right here and 69.5. So we're talking about 34% plus 13.5, 64 to 69.5. So 34, so let's add that. 34 plus 13.5 is 47.5%. Estimate the percent of women that are taller than 69.5. So I'm going to go to 69.5, and these are markings. These are like breakpoints. So everything to the right is somebody taller than 69.5 inches. 2.35%, 0.15. So 2.35 plus 0.15 is 2.5% of women. Estimate the percent of women that are taller than 64. 64 is the sample average, so it should be 50%, approximately. We're going to use our approximately symbol, 50%. Estimate the percent of women that are between 61.25 and 72.25. Oh gosh. So from right here, so 61.25, I'm going to mark it like that, up to 72.25. So don't include that 0.15. So we've got 34, 34, 13.5, and 2.35. So make sure you're marking 61.25 and 72.25. So let's add those. 34 plus 34 plus 13.5 plus 2.35. So we are saying 34 plus 34 plus 13.5 plus 2.35. So this is 83.85%. So just make sure that you are marking and not using all of the space. So that little tinge out the right, we're not including. What heights for women would be considered unusual? And we marked those. So anything outside of 2 standard deviations. So any woman that's shorter than 58.5 inches. So shorter than 58.5 inches, or, right, somebody taller than, let's look at our marking, taller than right here, 69.5. inches. So this lesson, we learned a lot. We learned about population and sample variance and standard deviation. We learned about skewedness. What is, we've talked about that in the last lesson, but we're going to kind of put that together. So if we decide that our data is symmetric, and that's how we can use the empirical rule, if our data is symmetric. If our data is symmetric, that means our mean and our median are approximately normal. Okay, that means the best measure of center is going to be the mean, and the best measure of spread is going to be the standard deviation. If your data is skewed in either way, either skewed left or skewed right, then our median is going to be the best measure of center, and our IQR is going to be the best measure of spread. So it's important for you to be comparing those, because that's going to help us make some decisions throughout the semester. So this lesson had quite a bit in it. Make sure that you are reaching out if you have any questions.